the basic concepts of linear algebra. And it's really these concepts are underlying the concepts that we introduce in linear algebra, but we've had this course on algebra. So algebra course, basics of commutative rings. You had 6 lectures with yesterday. It's I think it's all over. 6 lectures by all the lectures are over by Professor Vijay Kodialam. And the point is, I'm going to use some of the ideas there. I'm going to point very explicitly the relationship between those ideas which he has talked about and the basic concepts of linear algebra. Okay. So let me remind you what we did from last time. So here is the notation. Let's fix K. So notation. K is fixed field. K is a field. Let me write it. K is a field fixed. Once again, you can take it to be the field of real numbers or the field of complex numbers. That makes you more comfortable. If that makes you more comfortable, but it is for now any arbitrary field. V is a finite dimensional vector space over K, and T is a linear transformation, K linear map. In other words, a linear transformation from V to E. Okay. Now, the goal is to understand T. Right? What is the structure? So look, in words, if I expand this, see what is the structure of a linear transformation. Okay, so there are many. Okay, so let me now start to tell you some of the things you might that are part of this study of this structure. For example, we to go to a theorem which is sort of directly maybe makes sense for T. So let's assume K is algebraically closed. So for example, C, then we have the notion of Jordan canonical form. JCF, let me shorten it to that. Okay. So what this means is, so you have this, you classify, so let end KV denote the set or the algebra, let me call it the K algebra of all K linear transformations on V. So on this, we introduce on this. So let me give it a name. Let me use a different. So let's call it E. Okay. On E, we have as an equivalence relation. So T is similar to T prime if there exists G unit in NKV. So this G, okay, let me finish it and then I'll say it. So GT, G inverse is equal to T prime. Okay, now that's an equivalence relation. We can easily check. Now what this JCF does is, so the point of JCF, whenever you have an equivalence relation, so let me just draw this picture, this schematically. So let me do it in a different color. So imagine this is E. This is a very schematic picture, right? And you have, if you have, this is my set, the entire set, or which is an algebra. And once I have an equivalence relation, I get a partition of this set into pieces, right? These are the pieces, the parts. I mean, there need not be finitely many parts. I've drawn a picture that looks like it's finitely many parts, but you should take that with a pinch of salt. So the parts are the equivalence classes. So whenever you have an equivalence relation, there are equivalence classes, and they form a partition of on the set on which this equivalence relation exists. Okay. And so whenever you have such a thing, here is a problem. Identify in some way one element from every part, exactly one element from every part. Okay. What the JCF does is precisely answer this problem for this case. Okay. See, whenever you have a word form, or not whenever, but the word form is used in many different senses in mathematics. But one of the senses in which it is used is the following. If you have an equivalence relation like this, and then you have a method of identifying a unique representative from every class, then such a thing is called a form. The word form is one of its many senses in mathematics. One of them is to indicate this usage. So what the JCF does, is identifies unique representative from or in each equivalence class. Okay, so this is very useful because okay, let me say why. Before saying that, let me say one more comment and then make one more comment and then come to that. So end V, so this we did last time also. End V is the set of all linear transformations. Now you can add linear transformation. It's an algebra. We've said it's an algebra. What does that mean? Very loosely speaking, it means it's a ring. It's also a K algebra. There is a homomorphism from K into this. Okay, and it has further properties. The homomorphism must land in the center, etc. But which it does. But let's not worry about the word algebra. Let's use it loosely. Let's look at the. I'm not going to define it formally here, but let's look at some of the things, the attributes of NKV, which make it an algebra. So you can multiply, right? You can multiply by scalars by elements of V, which elements of K, right? And so this makes it into a vector space over K. This makes it into a vector space over K, which is also a ring. Okay, as we observed last time, this is isomorphic to M, D, K, where D is the dimension of V as a K-vector space. So we've assumed it's finite dimensional, so this D is a finite number. Okay, and this it's important to observe that this isomorphism is non-canonical. So let me put that in red. So this is non-canonical in the sense that it is not God-given. It involves a choice. Involves the choice of a basis. Okay, so now here's where the thing comes in. So there are many. So if you do choose different bases, you get different matrices. This is the set of D cross D matrices, right? So you get different matrices. Now, which one is the most natural one? I mean, there is no answer to that. Each choice is equally valid or equally invalid. Okay, so what's happening is precisely that if I fix a linear transformation and look at all matrices, possible matrices that can represent that linear transformation, what you get is precisely one equivalence class here. Everything in one equivalence class. They are all similar, right? Okay, observe that this G here, right? So I said a unit, there exists G, a unit in this. So units, let me go back to this color. Units is black. Okay, units in NKV are exactly the set, or form exactly the set GLV. So if I so this is the set of invertible linear transformations of V. Now, when we identify under this identification, now this is an algebra. This is an algebra identification, which means it respects addition, it respects multiplication, it respects scalar multiplication. This GLKV gets identified with the set of matrices GLDV or GLDK. So this is the set of, this is by definition D by D matrices over K that are invertible. As we know very well, invertible, you can check whether a matrix is invertible or not by means of checking, finding its determinant. Right? If it's 0, then it is not invertible. If the determinant is non-zero, then it is invertible. Okay, right. Okay, so so this is an example. I gave this Jordan canonical form. I don't know whether we will get there, but this is an example of what we mean by understanding the structure of the linear transformation. Okay, and So what we want to do is understand the structure of this linear transformation by means of concepts from algebra. Okay. Even when you define it with, even when you are doing it ordinarily in the sense of when you introduce it in maybe in your BSc classes, when students maybe are not so familiar with algebra, you are still using these concepts from algebra, but maybe they are not made so explicit. And the point here is that we're going to make them explicit. Okay. Okay. Any questions so far or comments? Also, any questions from what we did last time before we further move on?
Professor, what do you mean by the structure of a linear transformation? What it actually means?
Okay. So that's a very vague term. Okay. Structure means, I want to understand it as well as I can. Right. For example, if I give you one linear transformation, another linear transformation, and I ask you various questions about them, you should be able to answer. That's what it roughly means. I'm using the word structure in not a very precise mathematical sense, but in the usual English sense of the word, right?
I mean that, can you give to some extent the geometrical structure of a linear transformation? Does it mean that structure of a linear transformation that you are actually trying to mean?
Yeah, surely it involves definitely there is some geometrical. Okay, so you are saying whether it has meaning, it has anything to do with the geometry, correct? Is that the question?
Yeah. Yes.
Yes, absolutely. So for example, let us take K to be the set of real numbers, right? And then you have this linear transformation, and let's say it's diagonalizable, and you have eigenvalues, right? Then that means, and you have eigenvectors corresponding to these eigenvalues, and then that means geometrically you can describe the linear transformation as scaling by those eigenvalues along those directions, right? So this is roughly like the following, right? When we do analytic geometry, right, in high school, right, or higher secondary school.
Okay.
So we are doing algebra, right? We're doing a certain amount of algebra. When we solve two linear equations, right? Okay, let's do it this way. Linear algebra is also the subject of, or is the subject of, the study of the structure of solutions to linear equations. Again, I'm using the word structure, right? But again, in the usual English sense. Okay, so it is the study of solutions to a set of given linear equations, right? Now, let us take, for example, I take to take a simple example from high school. We have such a, solve. This could be an example in your NEET exam, right? Which is very much very topical these days. Everybody is discussing NEET exams. So something like this: x minus 3y is equal to 7. I wrote down some arbitrary, right? So this is a set of simultaneous equations. So you do some algebra, right? But then this has a geometrical interpretation, right? As we all know. Namely, that there is, right, this has a solution: x is equal to something, y is equal to something, right? I'm not actually going to solve it, but so what you have geometrical interpretation is, so you have this represents, each equation represents a straight line. So this represents this line maybe, and this represents this line maybe. So these are not drawn to, I'm not actually plotting these equations. These are schematic, okay? And the solution is finding this point, right? This is this point. So geometrical interpretation is you're finding the point of intersection of these two lines. Correct? So have I at least answered your question somewhat? Yes.
Professor, this we are clear, but as far as the linear transformation is concerned, we could not understand to this much amount of level.
No, but see, it's okay. Suppose we are, let's do it. Suppose you are solving it in 3 variables, right? What does it mean? You have planes in 3 space, right? And then you want to find the point of intersection of those, right? Or points of intersection, right? If it has multiple solutions, then it means points of intersection, right? The points that lie, even here, if these 2 lines happen to be parallel, or the same line in disguise, then you will get more points, right? So what I'm saying is that indeed there is a underlying geometry for this. Whenever we do linear algebra, there is indeed underlying geometry, and when I say structure, I do include the geometry, although in these particular lectures, we may not go into that part of it. Okay, so what I mean by structure here is something like answering this question, right? Well, what do we mean by the Jordan canonical form? How to find it, for example, or more simply, what is the minimal polynomial of T? What is the characteristic polynomial of T, right? So when we say what is the structure of T, when we associate something with T, it should be, and if I'm going to use matrices to attach it to T, then I need to make sure that there are different matrices that could possibly be attached to T, depending on my choice of basis, and it should be independent of that choice. So for example, when I say you can talk about the minimal polynomial of a linear transformation, right? Because, so how do I do this? I associate the matrix to T by a choice of a basis, and then take the minimal polynomial of that matrix. This is something we can do, right? But if I choose a different basis, I'll get a different matrix, and a priori its minimal polynomial could be something different. But we want to say, no, it's not going to be different, it's going to be the same, etc. So sorry, I was getting into more details there, but perhaps I have not answered your question satisfactorily.
I shall wait, Professor.
Sure, and keep repeatedly asking the question. I don't mind at all, right? Okay. I repeat. What I want to say is the following: that this, I am using the word structure in a very loose way. Let's go back to this way of putting it. I want to understand T, whatever that means, right? So when there is a new object, we want to say we want to understand this, right? And what does this understanding mean? It's not usually in a very precise mathematical sense, right? It's a vague sense. It means that if I ask you a question about it, you should be able to answer it or tackle it. That's what it means. And your point is well taken that there is an underlying geometry. And although we are not going to be in these lectures touching upon that very much, but indeed there is geometry, and that's part of this, what we mean by the structure. Okay. Sure. Any other questions or comments? Thank you very much for asking that question. I always appreciate questions and interruptions.
Thank you, Professor.
Yeah. Thank you for asking. Any other questions or comments? Okay. So last time what we had defined was the minimal polynomial. So minimal polynomial of T and we will this notation. So K is a field, V is a finite dimensional vector space, T is a linear transformation as above, fixed. And then what we want to do is make this V. So here is the main thing that will allow us to apply, here is the main idea that will allow us to apply algebra to this linear algebraic problem. When I say linear algebraic problem, I mean the problem of understanding T. Okay, so KT, this is the polynomial ring in one variable. That's our notation for it. In one variable, which is T, with coefficients in K. Okay, so turn, here is the idea, turn V or make V into a KT module as follows. So by letting T act, little t. So in order for it to be a KT module, okay, there are axioms for a module, but I mean, speaking a little loosely, what you want is every element of the ring must act on every element of the module. So what are elements here? So and of course we have the axioms of the distribution, etc. So this ring is made up of, when I say made up of, I should understand it correctly. I'm using words that are a little loose. So everything is a polynomial t, which means I take t, multiply it by itself several times, which means I take powers of t, multiply them by various scalars, meaning elements of k, and then add, right? That's what a polynomial is. If it is 5 plus 3t squared, then I take t to the second power, multiply t by itself, then multiply that by 3, and then add it to the constant 5. Right? So as you can see, if I tell you how t alone acts, I know everything else. Because how does t square act? Well, you let this t act twice, right? One after the other. And how does 3t square act? For example, then you act t and then act t again, and then act 3, the scalar 3, right? So because we know this is already a vector space, I know what scalar multiplication is, right? So it is enough to know how this little t acts, to know how this V becomes a KT module. Okay, so letting t act as t. That's the thing. Okay, once I do that, it becomes a module. Okay, and what you get is this map KT to, this is a ring map, ring homomorphism. Let me say even K algebra homomorphism. When I write hom, it means homomorphism. Okay, into this end K V, which we have identified with its non-canonical identification, MDK. You can also think in these terms, right? So D is also fixed. D is the dimension of V over K as a K vector space. Okay, right. So this is the important idea that lets us apply ideas of algebra to our problem. So as a first example of the application, we have defined the notion of minimal polynomial. So this is how you can do it. So look at this. So this is a vector space. So this is an infinite dimensional vector space. this is a finite dimensional vector space. And why? Because last time somebody answered this, but let me ask it again. What is the dimension of this over this? By now we should know this. This is equal to
d square.
d square. Very good. Because it's, for example, from here, it's clear that it's d by d matrices, right? That as a vector space. So when we write this, we mean as a vector space. Okay. So this has the point to realize is this has several structures. It's a group. It's an abelian group under addition of matrices. You can multiply matrices. So it's a ring. It's a ring with identity because there is the identity matrix which acts like the identity element for multiplication. Right? The commutation, the multiplication is not necessarily commutative. I mean, the moment d is bigger than 1, it is not commutative. Okay. So it's a non-commutative ring, but it's a ring with identity. Right? Moreover, it's a K algebra in the sense that there is a homomorphism from K into this, namely the scalar lambda you can associate with the scalar matrix lambda, scalar matrix whose diagonal entries are lambda. Okay, and if you do that, then it becomes also a K vector space. Or more directly, you think of this MDK, each matrix can be multiplied by scalars, right? So it is also a vector space. So it's a ring and it's a vector space. And you can talk, when we write this, we talk about, we are thinking of its dimension as a K vector space, and that's d square. Okay. Now, this is a ring homomorphism. It's also K algebra homomorphism. In particular, it's a K vector space homomorphism. In particular, KT to NKV is a K vector space homomorphism. Okay, so, but this is infinite dimensional, this is finite dimensional. So how can that be? Well, what it means is, it implies that the kernel, right? We have this first isomorphism theorem, right? KT by, so let's call this, let's give this a name. I think I called it rho last time, rho or something. Okay, so by kernel of rho is isomorphic to NKV. I don't know what this, which number is, it is, this isomorphism theorem, but you have an isomorphism like this, right? Okay. Now, which means this kernel of rho, which is an ideal here, kernel of rho, which is an ideal in KT, must be non-zero. It cannot be zero. Because if it is zero, then this becomes infinite dimensional, and that cannot be isomorphic to a finite dimensional space. Okay, and therefore this is a non-zero ideal, which means, but from what we observed last time, kernel of rho is equal to F. So kernel of rho has a unique monic generator. It is the least degree element, unique element, unique monic, non-zero element of least degree. And so that is my, so define the minimal polynomial of T to be equal to f. So this is in fact the correct definition of minimal polynomial. And when you define it in your linear algebra courses, this is in the background, but here we have sort of made it very explicit. Okay, let me pause here and ask if you have any questions. Okay, so the topic that I want to do today is the determinant trick. So let me ask you, did Professor Vijay talk about this at all? Anyone? Am I audible?
Yes, sir.
Yeah, okay. So did he do this at all? Did he use the word determinant trick?
No, sir.
No, okay. So he told me he might not have time to, so I haven't talked to him after these last 2 lectures, but let's do it ourselves too. So here, the basic idea is this. So the basic idea, so let me use a different color here and tell you the basic idea. Okay, so what I'm going to assume here, the prerequisite is that some properties of determinants, etc., that we learn in school, right? So if I give you a 3 by 3 matrix, I mean, or 4 by 4 or 5 by 5, although in school we restrict ourselves to 2 by 2 and 3 by 3 mostly. But given an n by n matrix or a d by d matrix, as in our case, with real numbers, say, then I can find the determinant. So the determinant is defined and it has several beautiful properties, right? So for example, if 2 columns of a matrix are the same, then the corresponding determinant is 0, right? And you have certain, you can add a multiple of a column to another column, and if you do that if you do that operation on a matrix, the determinant does not change. So the matrix of the determinant of the original matrix and the determinant of the transformed matrix, if you do this operation, are both the same, etc. Okay, so the first basic idea is that all this you can do over any commutative ring, right? So determinants of square matrices can be defined over any commutative ring, not necessarily a field. That's the first idea. Okay. Now, so there is also the notion of the adjoint matrix or the co-adjoint. I don't know the correct word. So how do you find the inverse of a matrix, right? So suppose I give you a matrix A, and let's say Aij, it's a D by D matrix, right? So how do you say with Aij in say R, right? How do we find A inverse, assuming it has an inverse? Anyone? Any method?
By cross Jordan.
What is that? What is cross Jordan?
The matrix A adjoined with identity matrix, and then you have to reduce, apply row reduced
Very good.
elementary row operation.
Very good. Very good. Okay, I understand what you mean by cross Jordan. Right. So you write this here A, right? And then you perform elementary row operations. Okay, and then such that you bring this, you try to bring A into this by performing elementary row operations into the identity matrix. And then what you see here, the output here is A inverse. Correct? Is that correct, Annamalai? Have I?
Yes,
Yes,
sir.
sir.
Okay. But this is a very practical, very beautiful way, efficient way of finding the inverse, indeed, right? But suppose I theoretically give you some matrix, some large matrix. So let's do this. Let's take a 2 by 2 and the 3 by 3 case. So what is its inverse? So there is this idea that so for each of these elements, you remove the row and the column. For each entry, you remove the row and the column and take the determinant of the n minus d minus 1 cross d minus 1 matrix. So here it would be D, right? Okay, D, and there is a I write in place of A, I write D. Okay, so here for B, so let's write this. Okay, sorry. So with each Aij, you associate the following: remove row I and column J, right? And okay, or I've written Aij here, but what you mean is with each not Aij, but with each I comma J. Okay, remove row I and column J from A and take the determinant of the remaining matrix. Determinant of the D by 1 cross D by 1 matrix. Okay, so let's call this something B sub Ij. Right? Okay, or let's call it little b sub Ij. The determinant is a number, right? Suppose this is b sub Ij. Okay, and then let me put this B, the matrix B, I define it to be minus 1 to the power I plus j into Bij. Okay, then take B transpose times A is equal to A times B transpose. And what you see here is the following matrix. This is determinant of A, determinant of A. It will be a scalar matrix. Okay, is this clear what I'm saying? Let's do this in this example. So what is B here? So can somebody tell me? So I must remove A, this column, this row, take the determinant, it's D, and minus 1 to the power 1 plus 1. So this is D here. Right? For B, in place of B, what do I get? Can somebody please tell me?
Just C. Minus C.
Minus C. Very good. In place of C, what do I get?
Minus B.
Minus B. And in place of D?
So it's A.
A. Right. So when I multiply, let's do A, B, C, D. This is A. Right. And let's do B transpose. So what is the transpose of B? D minus C minus B, A. This is the transpose of B, right? So I'm checking this. A times B transpose is equal to, if I multiply this, what do I get? Let's multiply it. AD minus BC, which is the determinant of A. And if I do this, A into minus B plus A into B, 0. Here C into D minus DC, this is 0. And this is AD minus BC. So indeed, this is checked. And you can do the other multiplication. That's also right. Okay. Now this you can prove just from properties of the determinant that you learned in school. So let's do a 3x3 case. So A, B, C, D, E, F, G, H, I. Let me put it like that. So if this is my A, what is going to be my B? Can somebody please tell me? Here, what should I write? I remove this column, take the determinant and multiply by this sign.
So it's EI minus HF.
Very good. EI minus HF. And what about the second entry? I should allow myself more room. So let me, okay. Yeah, second entry, please, here.
So it's GF minus DI.
GF minus BI. So let me write it as minus of, right? Because this minus to the power 1 plus 2. What you are saying, right? But I'm just going back one step. I plus j is 1 plus 2 here. That's a negative. And then times this sign times the determinant of this, which is DI minus GF. And if you expand it out, you will get GF minus DI. And what about here? It is DH minus EG or EG, right? Okay, very good. And let's complete this. Here, what do I get? So it's a minus or a plus?
Minus.
Minus. So the signs go minus, plus, minus, plus, minus, plus. They will alternate. Okay. Okay. So minus into BI
minus CH.
Minus CH. Very good. Okay. Here it's going to be a plus sign. Okay. And then I remove the row and column of E. And what do I get? AI minus CG. It doesn't matter whether you write GC or CG because the underlying things commute. We are taking it in a commutative. Okay. And here it is a minus sign. And it's the AH minus HG. BG, sorry. AH minus BG. Okay. Here it's a plus sign and it's BF minus EC. Here it's a minus sign and it is AF minus CD. And here it's a plus sign and it is DH minus EG. Okay. And you can check that if I take the inverse of the transpose of this matrix and multiply, then it has the property that when I multiply it with A, so let me here, it will have this property. A times B transpose is also the same as B transpose times A. And what you will get is a 3x3 matrix, of course, here with determinant of A along the, it's a scalar matrix with diagonal entry determinant of A. Okay. So this is, see, this is a very practical way of finding the inverse. This is very useful. Okay. But this is also true. This is a theoretical description of the inverse without doing any calculation, right? So we have defined this B, and we are saying that B transpose as this. So if I want the inverse of A, I take 1 over determinant of A times this B transpose. So A inverse is 1 over determinant of A times this B transpose. So of course, in order to define this, so this is, of course, if or assuming determinant A is non-zero. Okay. So clear so far? Any questions?
So this is the same method to calculate such as adjoint this B matrix?
Yes. This, in fact, this B, I forget the name. It's called adjoint, or some books call it co-adjoint. This is, in fact, this is the adjoint. Okay. I forget what the terminology is. Some of them, adjoint or co-adjoint. It's a name. I forget the correct name. But indeed, this is the theorem. Is this? If I do this procedure and look at define B to be this and take its transpose, then the inverse is given by 1 over determinant A into B transpose. Okay. Indeed, that's correct.
Professor, one more question.
Please.
The procedure suggested by Annamalai is normally considered as an optimal way for finding the A inverse, but you are saying this is the classical way is the better.
No, I'm not saying this is better, definitely. I'm not saying this is, see, we have multiple ways. So this is an abstract way of, so you're going to see the usefulness of this definition very soon. Okay, so this is, this observation has its own use theoretically, right? But practically, if I'm given the entries of a matrix, right, and I want to find the inverse, right, this is a much faster way, right? This will be a more efficient way. What is that? What's the name? Annamalai said something Jordan. I don't know the name. This procedure.
Jordan.
Yeah, but he used some other term before Jordan. Annamalai, what did you call it?
Cross Jordan.
Cross Jordan. Cross Jordan. Okay, right. Cross Jordan. Okay. So this cross Jordan method, whatever you call it, is a very efficient method to find the inverse given a particular matrix with numbers. I mean, if you're doing actually computation, for example, if you're trying to invert a matrix, if you're solving some differential equation or doing some numerical calculation and you want to invert a matrix and you want to write a computer program to carry out the inverse, you would use this procedure. You would try to code this procedure. Okay. However, okay, I'm not saying one thing is better than the other or anything like that, but there are two different things and both are useful in their given context. That's what I mean. Right. So there is also this alternate way of thinking about the determinant, right? You can, so see, I have abstractly written out how to write out the inverse, right? If you do this, I've given you a procedure in 3 lines. If you do this, you will get the determinant. Now, this may not be so useful to find actually the inverse. Okay. Maybe it is after you code this is more or less equivalent to this, but that's not the point here. The point here is that you have this theoretical, I mean, for lack of a better word, description of the determinant. Is that good?
Fine, Professor.
Yeah. Okay. Okay. So the point here, so here is the usefulness of this idea, is that this can be done. Okay. So the idea here is, now this procedure of finding BT, of this finding B and BT, can be done for matrices over rings. That's the usefulness. So you see, when I want to define this B, and a transpose is just taking the transpose, so that's not a problem. What operations are involved here? I am taking the determinant of this D-1 cross D-1 matrix, but determinant involves only addition and multiplication. It does not involve any division. The division comes only when I want to find the inverse, where you have this 1 over determinant of A here. But if I don't care so much about finding the determinant, finding the inverse, but given a matrix A over a commutative ring, I can find there is this matrix B transpose, which has this property. That's the point here. So the theorem, or if you want the observation, here is the observation or proposition which we have proved. If you want to call it observation, that's fine with me. So given a D cross D matrix A with coefficients in a commutative ring, the matrix BT defined as above has the property that A B transpose is equal to B transpose A is equal to determinant of A times identity. Okay, so this is the identity D by D matrix. So, and then a piece of notation. Okay, let's call it again. I don't know whether it's called adjoint or co-adjoint in some of the books, but let's define. I'll call it ADJ for adjoint. This is defined to be B transpose. So I can write this equation as, and this is the important equation here, A times adjoint of A. So this adjoint of A, given a D by D matrix A, this is also a D by D matrix. And it has the property that A times adjoint of it commutes with A. And when I multiply it with A, either on the left or on the right, since it commutes, I get the same answer in either case. What I get is determinant of A times identity. Okay, so this is the observation. Okay. Any questions? So here maybe is the, and let me emphasize it by saying in any commutative. Okay. Okay. Now let's get back to our let's get back to our context and use this determinant. Okay, so as usual, we have K, which is a field, V, which is a finite dimensional vector space, T is a linear transformation, D is the dimension of V over K, and we have made, V has been made into a KT module by T acting as T. Okay, right. Okay. Now, you see, what is the so we can write the following. So we are going to use the matrix notation a little creatively. So we are going to use slightly extended matrix notation here. And I mean, if I don't point it out, you won't even complain. So we're going to use that notation, but it's really an extend. You're going to extend that notation, right? This often happens in mathematics, right? When we use some notation and then we extend that notation to other contexts. That is a very useful way of doing that's a very useful technique. Okay, it's a useful thing to do. Okay, so let's fix, let v1, v2, vd be a basis of v. Okay, I fixed that. Okay, now if I take this, I'm going to write a matrix like this. So T, V1, V2, VD. So what do I mean by now here? So this is T acting on V1, T acting on V2, T acting on VT. Of course, this is, so remember that TVJ is nothing but capital TVJ, right? And if T is the point, so if T, if let, what do I call it? Let C be the matrix. Let me call it C. Let C be the matrix of T with respect to V1, V2, VD. Then tell me what this is, please. What is TVJ equal to? If T is C is the matrix of T with respect to V1 through VD, then T times Vj is equal to I'm hearing a deep silence. In terms of the matrix C, could someone tell me what this is? How do you find the matrix C?
The jth column of C.
Yes. So could you exactly? So could you? So what is this? C1 J V1 plus C2 J V2 and so on, right? Correct?
Yes, sir.
Correct? Okay, that's what I wanted. So if you write this out, what this is you will see here C11, C21, etc. So this is C21, CD1, C21, C12, C22, CD2, C1D. Sorry, did I? Just one second. T V1 is equal. Okay, I want to write here V1, V2, VD. Yeah, C1D, C2D, CDD. Yes, I've written it correctly. Okay, so this is what it turns out to be, right? So this is, observe that what I have is T times V1, V2, VD is nothing but this C transpose. I've transposed this C into V1, V2, VD. Now, which I can write as, if I again creatively use this T times I minus C transpose into V1 through Vd equal to 0. Okay. Now, what is this? This is a D by D matrix, right? With entries in KT. Right? What is it? It's actually T minus C11 minus C21 minus CD1 T, C12 T minus C22, etc. Okay. Now, here is the idea. Now you can multiply this by its adjoint. So call this A. So I call this A. That's why I used a different letter here. I want to call this A, right? And I want to multiply this by the adjoint of A. So if I do that, so multiply, and this is the determinant trick. This is the determinant trick. This is an illustration. So multiply by adjoint of A on both sides. So what you get is adjoint of A times A into V1 through V1, V2, Vd equal to 0. When I multiply by adjoint of A, this is a 0 matrix, 0 D cross 1 matrix. So what I get still get 0. But what is this? This is determinant of A into I by our observation above. So what I get is determinant of A times I. So you can I times V1 through Vd is Vd itself. So V equal to 0. Now this is an element. So this is an element of KT. And what we are concluding is that this element kills V1, kills V2, kills Vd. So the conclusion is this element determinant of A, which is an element of the ring, underlying ring, kills V1 equal to determinant of A, V2 equal to ... equal to determinant of A into Vd equal to 0. All these are 0, which means so if it kills every basis element, right? And of course, this is being an element of the ring, it commutes with scalar multiplication, commutes with scalars. So what this means is determinant of A kills V. But what is determinant of A? Look at this, right? So the determinant of A finally, determinant of A is determinant of Ti minus C transpose. Now, if I take the transpose of this, it is the same as Ti is a diagonal matrix, so that remains Ti. The transpose of C is C, this C. And what is this? This is nothing but the characteristic polynomial of T. So what's the conclusion? The characteristic polynomial of T kills V, which means this is the Kelly-Hamilton theorem. So CH is proved. QED. Okay, so yeah, now let me, that's it for the day. I don't want to speak anymore, except I want, in the remaining few minutes, I'll let you ask me questions and let us try to understand what we have just done better. So what we have done here is Okay, is this equation okay? What we have done here. So let's try to understand it step by step. So is this okay?
Yes, sir.
Okay, and see if C is so I know the matrix of C with respect to C. How do I find, first of all, how do I find the characteristic polynomial of T? Right, I take C, take determinant. So do you agree? So this is, I like put all the explanation in this color. So okay, so determinant of Ti minus C is the characteristic polynomial of T with T as the variable. Do you agree with that? That's the, so sorry, not A. I shouldn't write A here. C. C is equal to matrix of T with respect to some basis. It doesn't matter which basis, because if I choose a different basis, all these matrices will be, any other matrix C will be similar to C, and therefore, if I take that will be similar to this matrix, meaning if C prime is another matrix, then Ti minus C will be similar to Ti minus C prime. Okay, and therefore, if I take this determinant, it's not going to matter. I'm going to get the same answer. So, do you agree that this is the characteristic polynomial of T? This is how we define it, right? Correct? What we have is here is that same matrix, except that there is a transpose. That's all. Okay, so from here to here, is this okay? So this is explained by this equation, right? TVJ is equal to C1J V1, C2J V2 plus CDJ VD. That's precisely TVJ. That is the jth column, jth row of this matrix, TVJ. And if I take the jth row of this matrix, it will be C1J V1, C2J V2 plus dot 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 plus CDJ, the last element here in the jth row, times VD. That's precisely this. So this, if I write, there are D equations like this: TV1, TV2, TV3, etc., TVD. And if I collect all those equations together, I can write it in matrix form like this. Is this all right?
Yes, sir.
Okay. And that is just this, right? Because this matrix here is just the transpose of C, right? Here it's C11, C21, CD1. So here is the first row of C, here is the second row of C, here is the dth row of C. So that's C transpose, correct? And here is this matrix, this is the usual matrix, except so this is, you won't complain about this at all if these had entries over a field. What I'm now doing is sort of extending it to matrices with entries in a ring. That is the extension. So instead of this T, action of T, I think of the action of the matrix T times I. Right? So this is actually T times I, no difference. And then I bring this matrix to the other, send this to the other side and write it as Ti minus C transpose into this. Now think of this as a matrix A. I multiply by the adjoint, and then I get this. Yeah, you please ask if you have questions, please do ask. I am done with my explanation. I mean, it may seem like magic, and you may have to go back and sit down and digest it. Like with any good mathematical idea, it takes time to digest, but it's a really beautiful idea. Very simple, and people take it for granted, of course, once you know it, but it really is a beautiful idea. Okay, I am done. Guruswami, I'll send you the notes of these lectures. I'm happy to answer questions, but since I'm not hearing any questions, I'm saying this. I'm happy to be here and answer questions. Maybe people are maybe shy to ask questions with the video being on, I mean, our recording being on. Maybe Guruswami, if you could, may I request you to, yeah, very good. Okay. Now the recording is stopped. We are free